Okay, so today we will continue to talk about forward kinematics. Before we start to talk about the analysis of robotics, so let me show you a video that is pretty fun. Okay. This is an example of how to use industrial robotics in manufacturing.
Facilitating industrial production for over 60 years, FANUC is present in 120 countries, including Hungary, assisting key sectors like the automotive industry, for example, at the Audi Hungaria Motor Limited factory in Győr, where they are developing and manufacturing cars for the Audi AG and the Volkswagen Group. Audi Hungaria is one of the companies with the largest turnover and export in Hungary, producing 2 million engines and 100...
Constantly improving our production and
okay,
robots
so this is kind of an advertisement, but I would like to show that in the industrial robotics, they are actually using these robotics to carefully control the final tooling and the position and the orientation of the final tooling, so that at each time point, the robotic arms, they can accurately achieve the position and do the task. Okay, so that is the goal of our robotic analysis. So again, in the beginning of the robotic analysis, we mentioned that there are two questions we're trying to solve. One is that if we know all the joint variables, means we know all the theta, all the orientation of all the joints, what should be the final orientation and position of the end tooling? Okay, that is the first question. And the second question is, if we want to achieve the desired position and orientation of the tooling, what should be the joint variables we gave, which is the theta and the prismatic joint, that is the motion. Okay, so if, for example, if we use Arduino and we can control the motor, and each motor can be used as the actuation for the joint, right? And it can give a theta, right? It can give the theta. So in a robotic arm, for example, there could be 5 joints. It means we can use 5 Arduinos to control 5 motors. Okay, so now from the first half of the semester, we already know how to control the motors and how to generate these joint variables. So now the question for the robotic analysis is that how we're going to connect multiple motors, which means multiple joint variables, to finally achieve the goals, right? Which is the final position and orientation of the end effector, which is the tooling. Okay, so in the robotic conventions, we have learned that, okay, so in a robotic arm, there could be n links. N links means the n rigid bodies connected by the joints, right? And so they're connected by the joints, and each joint can be defined as a coordinate, right? And say if we have n joints, then we're going to have n coordinate frames. And also, we will need to have one extra for the tooling. Okay? So, the question is how we're going to use a unified method to connect all these frames. So that is the question we're trying to solve for the robotic analysis. Okay. So this comes to the method called DH convention, which is Danovic-Hartenberg convention. So this method provides a general methodology so that we can do the analysis between any 2 frames, okay, of the joints. Okay, so that by this convention, and it defines 4 parameters, so that for each step, each 2 frames, we know 4 parameters, and then we can finally do the analysis of the final frame of the end effector with the reference of the base, which is the world coordinates. That is the final goal we want to achieve, right? So which is T, N, 0. Okay, So 0 is the coordinate frame of the base, and it is also the world. It also represents the world coordinates. And n is the n effector. Okay, so with this homogeneous transformation matrix, actually it represents at every n effector what is the orientation and position of the n effector in the world space. This is the final question we're trying to answer for both forward and inverse kinematics. For forward kinematics, we know all the theta 1, theta 2, theta 3 if they're all revolute joints with motors, or the di, d1, d2, d3 if they're prismatic joints. Okay, so if we know all the joint variables, then what should be my final t and 0? Okay, and t and 0 means the n effector in the world. Okay, so let's go back to the DH convention. So what is that? So the DH convention, it provides a systematic procedure for forward kinematics analysis. Okay, so it means that once we get the point of DH convention, and we can quickly do the analysis between two frames. And this DH convention is widely used for selecting the reference frames. And each homogeneous transformation is represented as a product of 4 basic transformations. So that is how we define the DH convention. Okay? So in rotation matrix, the Euler angles, we know that if we want to represent a arbitrary orientation of two frames, we need to know at least 2 independent quantities. And now it goes to the homogeneous transformation matrix. If we want to understand the relationship, means the orientation plus the position between two arbitrary frames, we need to know 4 independent quantities. Okay? And these 4 independent quantities can be defined this way, so that we can use 4 variables to represent one transformation. Okay? And these 4 steps are that, first of all, we need, this is, for example, we want to do the position and orientation from frame 0 to frame 1. So there are 4 steps we need to do. The first step is we need to rotate from Z0 to Z1. We need to rotate from X0 to X1 along the Z-axis. And then we need to move along the Z0 axis with the distance d. Okay? And then we need to move from this point to the final position and with the distance of a, and then finally we rotate around the x1 axis with the angle alpha. Okay? So we assume that if we want to do the transformation between 2 arbitrary frames, we can always follow these 4 steps, so that we have the theta I, di, ai, and alpha I. We can use these 4 quantities to represent a arbitrary transformation. It's like you use Euler angles to do the rotation of any rotation, right? Okay. So for DH conventions, if we want to use this method, these 4 quantities, we actually need to have 2 assumptions. The first assumption is that we assume x1 is perpendicular to the z0. Okay, so it means x1 must be perpendicular to z0, and x1 must be intersect with z0. Okay, so means this axis and this axis, they must have an intersection so that we can find out the D and the A. Okay, and then with these two assumptions, so it means we add constraints so that finally, if we want to achieve these two frame transformation, we can use four parameters. These four parameters, which again, they're theta I, di, ai, and alpha I. Okay? And these four, again, in each step, it is a basic transformation. Basic transformation means either it's just only one action, either a rotation, one-step rotation, or one-step translational motion. Okay? And with these four steps of basic action, we can quickly use the basic transformation matrix, which we have learned in the last lecture, and so that we can in the lecture of transformation, so that we can quickly use these four formatting of basic transformation. And this one is the rotating around z-axis with theta, and this is translational motion along z-axis with di, and this is translational motion along x-axis with ai, and this is the rotation around x-axis with alpha I, so that we can quickly write these four basic transformation matrix. And for example, these two, this one and this one, they're translational motion. This is along z and this is along x, so that we can get these four basic transformation matrix. And then we calculate the multiplication of these four matrices so that we have the final results. Okay, and in the future, we will directly use this AI, this matrix directly. So in this matrix means for a arbitrary transformation from one frame to the other frame, we can always use four parameters to represent that, which are theta I, which is here, and alpha I, and di, and ai. Okay, so once we can find out these four parameters, then we can quickly use ai, which is the homogeneous transformation matrix from I to I minus 1, right? Okay. So then let's go back to talk about what are these four parameters in a robotic arm, in a robotic manipulator. Once we know these four parameters, these physical definition of these four parameters, then in the future robotic analysis, we can quickly write down these four parameters from the geometry, the robotic arm geometry, and then we can use AI directly, right? AI matrix directly. And then we can calculate the final T and 0, which is our final goal. Okay, so what are the four parameters? Okay, the first parameter is AI. AI is the distance between zi minus 1 and zi along xi axis. Okay, so that means along xi axis, which is in this case is x1, and that is the distance between z0 and z1. So actually it shows the distance of z0, which is here. If we just count the distance along xi axis. Okay, so here we have our z0 and z0. If we just consider the projection to the position of that and the xi in the x1 axis, so which is here. Okay, and then the position of z1, this is the position of z0 on the xi axis. And this is the position which is the origin of the z1, and that is on the x1 axis, because x1 is perpendicular to z1 is perpendicular to x1, so if we count where is it, so it is here if it is considered on the x1 axis. Okay, so it means that our AI is z0 to z1 on the x1 axis, so that is our A. Okay, so which is this distance, A. And if we consider the robotic arm connection, so for example, here we have joint and here we have joint. Again, if we define the joint from 0, we define the joint from 1 to n, right? 1 to n. And then the coordinates, the coordinate frames, that is corresponding to 0 to n minus 1. It means if we call this joint I, and then the coordinates for the joint I is frame I minus 1, okay? And then, so that we will have the frame n for the n effector. That is how we define the robotic convention. Okay, and then the link, we define that from 0 to n, right? From 0 to n. It means the joint n is connecting, the joint 1 is connecting 0 and 1. Joint I is connecting I minus 1 and I. Okay? So, then my A means on my xi axis, my position between zi minus 1 and zi, okay? So which is this distance in this case. Okay, that is the first parameter. The second parameter, alpha I, it means the angle rotating from zi minus 1 to zi, okay? So it means my z0 rotated to, if this is my z0, if we parallelly move this thing to this position, and so this is going to be my z0, right? My z0 is pointing here, and I move it to here so that I can find out what is the angle between z0 and z1, okay? So my alpha means the angle between z0 and z1, okay? So here I have my z0, and this is my z1, and this is the alpha, and it must be on the plane that is normal to xi, okay? So it means on this plane, here I have my alpha. Okay, and what is di? Di means the distance from the origin of O0 to the intersection of xi and zi minus 1. In this case, that is z0 and x1. Okay, so this is my intersection. Okay, and so from my OI minus 1, in this case is O0 to the intersection, and this is my D. And then it goes back to the robotic arm, and then the thing means we have along zi minus 1 on the zi minus 1. Where is my OI minus 1 and OI minus 1 to the intersection? Intersection is, here I have my zi minus 1, and here I have my xi, so here I have the intersection. So it means from OI minus 1 to the intersection, I have my DI, okay? And the joint angle theta I means the angle from xi minus 1 to xi, okay? So in this figure, that is clear to see, and the angle theta I, it means from x0 to xi, and where is my xi? If that is pointing to this direction, and if we just consider on this plane, so this is gonna be my theta I, okay? So here in the robotic arm, it means, again, that means from xi to xi minus 1 to xi, so which is here, it is this angle. Okay. So that is the DH convention to define these 4 parameters. So the key thing for forward kinematics analysis is to find these 4 parameters. Once we have these 4 parameters, we can quickly calculate the AI by the given matrix. Okay. So a few things we have to emphasize. The first is that for the revolute joint, the theta I is the variable, means this is changing. Okay, so means we are controlling the theta I, for example, using a motor. And the other 3 parameters are constant because they are determined by the robotic geometry. And for a prismatic joint, the DI is the variable because this is changing. And for example, we can also use either motor or other type of linear actuator to give this DI. And the other 3 parameters, which A, D, and alpha, they are constant. Oh, sorry, A, alpha, and D, they are constant because they're determined by the robotic geometry. Okay, and the positive sign, okay, the positive sign for the alpha is from Zi minus 1 rotate to Zi by the right-hand rule, means if if it is by the right-hand rule, and so here we have our right hand, for example, this is our right hand and this is our thumb, and this is the rotating direction, and this thumb is pointing to the rotating axis. Okay, and means this is positive. So if we, in this case, if we use right-hand rule, and we already know that this direction is positive. So once this pointing to this direction, it's going to be negative. Okay. And the positive sign for theta is from xi minus 1 to xi by the right-hand rule. So again, that is, we have the hand, and here we have our hand, and that is our right hand. So it means that we have our hand like this, and this is our thumb, and these are the rest of our fingers. And so this is our right hand, so you can use our right hand to show that. Okay, so it means this is the rotating axis, and this is the rotating positive sign. Okay, so it means we already defined this as positive, so if it is the rotating is opposite, then that's going to be negative. Okay, so here, please don't worry. Later, we will do a lot of examples. So you will see in the real robotic arm how we're going to find these 4 parameters. So don't worry. But these are the basic definition of how to find these 4 parameters. Okay, so let's see one example. Okay, so for this example, that is a planar elbow manipulator. It's pretty simple. That in this case, we have 1, 2, and right here, we may consider that as the end effector, okay? So the frame 2, that gonna be the frame, the coordinate frame for the end effector, okay? And these two, here we have the joint 1 and joint 2, so we have frame 0 for joint 1 and frame 1 for joint 2. Okay, so then we define this 2 and 3, we have 3 frames, okay? Because we have 2 joints, so that we have 2 frames, and we have 1 extra frame for the end effector. Okay, and then the first step for solving forward kinematics is to find the 4 parameters. Okay, so here we read as link 1, and link 1 means the frame 0 to frame 1. Okay, the coordinate frame, okay? And this is link 2, and link 2 means the frame 1 to frame 2. And at each step, we need to find 4 parameters, which are AI, alpha I, DI, and theta I. Okay. So the first step is to find the 4 parameters for link 1. It means the frame 0 to frame 1. Okay. Here I have my frame 0 and I have my frame 1. Okay, so here I have my frame 1. And obviously the ZI is pointing outside the paper. So here I have my Z1 and here I have my Z0. Okay? And another thing I want to emphasize again is that when we actuate the joint 0, joint 1, okay? And joint 1, we have the frame 0, okay? So which is here. This is our joint 1. And joint 1 has the coordinate frame 0. Okay, so if we have a motor here, for example, if we actuate joint 1, we are actually moving link 1, okay, which is here, okay. So it means that if we give a actuation right here, we are actually, because this is a revolute joint, so we're actually we'll generate the theta 1, okay, theta 1. Theta 1 is for the rotation of link 1. Okay, so here I want to emphasize that. So although the theta 1, we need to find it from the frame 0, but it is theta 1. Okay, so let's start to find these 4 parameters. Again, what are the definitions for these 4 parameters? Again, let's quickly review. AI is ZI minus 1 to ZI along XI. Okay, so in this case, that is the position of between Z0 and Z1 along XI, which is X1 axis. Okay, so here we have our X1 axis, so which is here. Okay, and the displacement, which is the distance between the Z0 and Z1, so we can quickly find, okay, so here I have these 2 axes. So this distance is my AI, right? That is along XI axis, the distance between Z0 and Z1. Okay, so that is A1. Okay, and what is the definition of alpha I? And alpha I is the rotation from ZI minus 1 to ZI. Okay, and in the plane. Okay, so here the Z0 and Z1, they're parallel. So obviously we have 0 because they're parallel. Okay, and how about the next one, DI? What is the definition of DI? DI is the OI minus 1, right? Which is the origin of the frame 0 to the intersection, So the intersection here, intersection of X1 and Z0, okay? So intersection, and seems like, okay, so DI means the OI minus 1 in this case is O0 to the intersection of XI and Z0 along ZI minus 1 axis, which is along Z0 in this case. So seems like, okay, so they're in the same point. So my DI is 0. And then what about theta I? What is the definition of theta I? So the definition of theta I is xi minus 1 rotate to xi. Okay, so where is my x0? So my x0 is here, and my x0 rotate to x1. Okay, so seems like that is theta 1. So I have that as my theta 1. Okay, and because this is a revolute joint, so theta 1 is my joint variable. So I mark star for joint variable. It means it's not a constant. It is a variable that is controlled by the motor, and which is given by the joint. Okay, and then how about the next step? Next step, it is from frame 1 to frame 2. Okay, so here I have my frame 1 and I have my frame 2, and frame 2 as my the coordinate frame of the end effector. But anyway, I can use the same method and definition to find these 4 parameters. Okay, and the AI is zi minus 1 to zi along xi axis. So that means along x2 axis, the position between z2, z1, and z2. Okay, so z2 obviously that is also pointing out of the paper, so I have my z2, z1, and z2 along x2 axis. Okay, so this is the distance between z1 and z2. Okay, so that is a2. And my alpha I again means the rotation from z1 to z2 in this case, and they're parallel, so that is 0. And di means the distance between OI, in this case that is O1, to the intersection of z1 and x2. Here I have my z1 and x2, and they're at the same point, so my di is 0. And then the last one, which is theta I is the angle rotate from xi minus 1 to xi. So in this case, that is the angle rotate from x1 rotate to x2. So that is theta 2. And again, this is a revolute joint, and the joint variable is theta 2. So theta 2 is my joint variable, and I use star to show the joint variable. And the rest of 3, okay, so these are constant, and these constant are determined by the geometry of the robotic arm. Okay, so again, in each step there is only one joint variable, and all the others, they must be known, and you must be able to read it from the robotic geometry. Okay, so now I can quickly, once we are familiar enough with these 4 parameters, we can just quickly read the coordinates between 0 and 1, 1 and 2, and then we can quickly read these 4 parameters. Okay, so that with these 4 parameters for every step, we can write down the homogeneous transformation matrix for each step. And A1, it actually, if we use transformation matrix, that is, we actually, in robotic convention, we use T instead of H. So that is T1, 0. Okay, T1, 0. And we write as A1. Okay, so here, this is my AI matrix, which we just talked about it in the DH convention. Okay, so which is directly given with the 4 variables. Okay, so now we just plug in these real numbers so that we can have A1 and A2. Okay, so if we want to calculate A1, and we need to plug in these 4 parameters, so then my AI becomes A1, and my alpha I becomes 0, and my theta I becomes theta 1, and my di becomes 0. Okay, so my di is 0, so I have my 0, 0, 0, 1, which is my 4th row, must be 0, 0, 0, 1. And here, di is 0, so I have it at 0. And then we calculate from the first term, that is theta, right? Cosine theta I. Now we know theta I is our joint variable, so I just use theta I. So it's short as C1, and C1 means cosine theta 1. Okay, and then this term is sine theta 1, so that is S1. I write as S1. Okay, and my alpha I is 0, so cosine 0 is 1. Okay, so I have my negative S1, and here I have my cosine theta 1, so that is C1. Okay, and here this term is sine alpha I. Sine alpha I is sine 0, that is 0. Okay, and this term I have sine theta alpha I, so which is sine 0, so this is 0, this is 0, and cosine 0 is 1, so I have 1, and these two is AI times A1 in this case times cosine theta 1. Theta is my joint variable, which is not constant, so I have to write it as theta 1, okay? And this is A1 times sine theta 1. Okay, and my A2, again, I use the same definition of the matrix, but I plug in these four parameters, these four values, okay? And then I have now my theta I becomes theta 2, so I have my C2, S2, and 0, 0, and my alpha I becomes alpha 2, which is 0, again, which is 0, so I have my cosine 0 is 1, so here becomes negative sine theta 2 and cosine theta 2, and 0, 0. And here, again, this is alpha 2, but sine alpha 2 is also 0, so sine 0 is 0, so I have 0, 0. And this is cosine 0 is 1, and I have 0. And this is A2 cosine theta 2 and A2 sine theta 2, and 0, 1. Okay? And then my final homogeneous transformation matrix is T2, 0. My T2, 0 equals to A1, A2 by definition, and that is this matrix multiply this matrix. So that is two matrices multiplication. So then I can calculate it directly. So that is the first row times the first column, first row times second column, and then have blah, blah. And so you will be able to calculate the 16 variables, 16 terms, okay? So here, after my calculation, this is going to be cosine theta 1 times cosine theta 2 minus sine theta 1 times sine theta 2, which is the first term. Okay, so that is equivalent to cosine theta 1 plus theta 2. So I write as C12. That is for C12 means cosine theta 1 plus theta 2. And I write S12 means sine theta 1 plus theta 2, okay? And after these two matrix multiplication, here I have cosine theta 1 plus theta 2, and this is negative sine theta 1 plus theta 2, and this is sine theta 1 plus theta 2, and this term is cosine theta 1 plus theta 2, and this term is 0, and this term is 0, and this term is A1 times C cosine theta 1, which is short as C1, and plus A2 times C12, and this term is A1 times sine theta 1 plus A2 times sine theta 1 plus theta 2, which is S12. And this is 0, 0, 1, 0, and 0, 0, 0, 1. Okay, so if you calculate the 16 terms, you will be able to find this matrix. Okay, so that is my calculation. Okay, so the interesting thing is, let's go back to the 2 frame. We'll just consider my frame 0. Okay, so here I have my x0 and y0, and this is my base frame, right? My base frame, which it is also equivalent to the world space. And finally, I have the first link and the second link, and here I have one joint, and here I have another joint, the second joint, okay, joint 1 and joint 2, and then here the frame 2, it is representing the AND effector, right, the AND effector, okay, and I draw my coordinate 2 for the AND effector, okay, so here I have my x2 and y2. Okay, so then what is the physical definition of T20? We calculated from the T20 equals to A1 times A2, okay, times A1 times A2, okay. My T20 equals to A1 times A2, and that means my AND effector's orientation and position in the base frame with the reference 0, okay. So by definition, it should be R20, D20, 0 and 1, right? By definition. Okay, so here, if we consider, we go back to take a look at what we have calculated. And obviously, these 9 terms is R20. And that is interesting. The format is the same as the rotation around z-axis, with the angle theta 1 plus theta 2, right? Okay, so if we're familiar with the basic rotation matrix enough, and if you cannot remember that, then please go back to the slide and take a look. Okay, and these 3 vectors, these 3 elements is the vector of displacement. Okay, so if we go back to this drawing, and so we will be able to see that, okay, so what is this position? Okay, so this is A1 and this is A2. From the geometry, we can, if we define the thing as x equals to A1, this is theta 1 and this is theta 2, and A1 times cosine theta 1 plus A2, and projected to the x0 axis times cosine theta 1 plus theta 2, right? And because this is theta 1 plus theta 2, okay? And if we define this distance as y, and y equals to A1 times sine theta 1 plus A2 times cosine theta 1, because it's y, is sine theta 1 plus theta 2, okay? So if we use the C and S to write down that, and this can be written as A1 times C1 plus C1 means cosine theta 1, okay? And A2 C12 means cosine theta 1 plus theta 2, okay? And this is A1 S1 plus A2 S12, okay? And so it directly shows if we move the origin of frame 0 to the origin of frame 2, so we actually move x, y, right? Okay, so it seems like that is physically, it means this definition, okay? So that is equivalent. So again, I want to emphasize that for the DH convention, we use 4 parameters. The first step is to find 4 parameters for each step. And then step 2 is we plug in these 4 parameters for all the AI. And step 3 is we calculate Tn0 equals to A1 times A2 times all the way times n. Okay? And physically, the t and 0 means the n effector's position and orientation with the reference of the world coordinates, which is the base. Okay? That's it. So now I believe we have a better idea of how to find these 4 parameters from the robotic arm. So let's see something more. Okay? Okay, so in the previous example, we already gave okay, so now in the previous example, which is here, okay, this example, we already gave the 3 frames. So now in the real robotic arm, which we have seen some examples in the video, right, in the YouTube video. So we have seen that for different robotic manipulator, to do the analysis, the first step is we have to extract the coordinate frames by ourselves. And that is a little bit tricky. Okay, so for each coordinate frame, that is corresponding to 1 joint. And 1 joint can be controlled by a Arduino, right, with a motor. Okay, and in the future, if we deal with more complicated robotic arm, we're not really using Arduino. We can use, for example, Raspberry Pi, and we can use the ROS in the Raspberry Pi. But anyway, each joint can be controlled by a motor, and this motor can be controlled by something. Okay, and so if we talk about the overall robotic arm analysis, first of all, we have to define the coordinate frames by ourselves. So for example, I just directly give you a robotic arm, and you just take a look at geometry and take a look at the real robotic arm, and we want to do the analysis. But first of all, we need to define the coordinate frames, one frame for each joint, so that we can start the analysis. Okay, to assign that, we have 4 steps. The first step is we need to assign Z0 to Zn-1. That is corresponding to joint 1 to joint n, right? Okay, so Zi is the axis of actuation for joint I plus 1. Because for joint I, that is Zi minus 1, okay? So the numbering system of the joint is always 1 more than the frame numbering system, okay? And then the second step is we need to assign the base frame. So although the base frame assignment is arbitrary, but we always assign the base as the base frame, okay? So which is the frame 0. And so again, we have to recall some robotic conventions. If joint I is actuated, the link I moves because the joint I is always connecting the link I minus 1 and the link I, okay? And this is the frame, this is the joint I, okay? Joint I. But it is frame I minus 1, okay? And so if we actuate, means for example, we have a motor and we give the variable of this motor, which is for the joint I, and then we're actually moving the link I, okay, which is the next link. And also assigning ZI is arbitrary, but it is not unique. Means we have multiple ways to do that, okay? But finally, the final transformation from the base to the end effector will be identical. So means the final frame, which is my frame, okay, so which is my frame N to frame 0, it should be identical. Means although it's something in between, we could have different methods of defining the bases, defining the frames, but anyway, we will be able to have the same T and 0, okay? So again, for the forward kinematics, we care the final T and 0 because this means my end effector orientation and position in the frame 0, which means in the world coordinates. And this is we really want to see because, for example, in the video, if we want to control the robotic arm in the manufacturing in whatever tasks, okay, we actually need to know at each time point, at each world space location, what is the tooling, okay? And then the step 3 is to assign the frames in between, okay? And there are multiple cases. So when the frame 0 is established, which is the base, we already established the base, and then the frame in between, which is frame I, can be defined in an iterative process from the previous frame I minus 1. Okay, so it means when we define frames one by one. Okay, and we have different cases to name and define the frame. The frame means xi, yi, and zi. Okay, and there are 3 cases showing the different type of geometry, and it looks complicated. Here I want to say that here, please don't worry, and we will see lots of examples in our lecture. So it means that although we're not be able to understand it in a first glance, but when we do enough examples, you will see how we extract the frames already, so that we will be familiar. And then once you see those prismatic joint or the revolute joint in the robotic arm, we will be able to define that. Okay, so I will skip this part. My strategy is we just do the examples first. Once we are familiar enough, and we will be able to give these frames. Okay, this step 4 is to define the end effector, which is the frame N. Okay, and frame N, we use a new frame to define the end effector. And the end effector and the origin is usually placed symmetrically between the fingers. So for example, in this case, my end effector is a finger. Okay, it's a grasper. And I define the origin in the middle. Okay, and the unit vectors, in this case, I define the unit vectors as x, y, z, but my x is pointing inside, and my z is pointing along this axis, which is kind of like approach, right? And my s is in this direction, which is perpendicular to the approaching direction. So that is kind of like a sliding. So, and this final frame, this final end effector frame N, that is defined based on the geometry and the end effector. Okay, so once your end effector, for example, this finger is rotating or moving or sliding, but my frame N is always corresponding to the the end effector, which is the geometry of the end effector. Okay, so for example, now if I move my fingers in this direction, and then I'm gonna have my frame N in this direction. Okay, so here I have my origin in the middle of the grasper, and still I have my Zn that is pointing to the approaching direction, and my Yn is the sliding direction. Okay, so only if we define the frame N just for the grasper, which is in this case that is a finger, then once we understand the T and 0, we can quickly understand what is the orientation and position of my end effector in the world base coordinates. Okay, so that is how we assign the coordinate frames. So today I will have to stop here, and then next lecture we will talk about enough examples, then we will become familiar with the frame assignments as well as the finding the 4 parameters and find the final forward kinematics matrices. Okay.